Hi guys, welcome to 8.2 ellipses. And for today's warm-up problem, I want to talk about how you could maybe define a circle. And since I can't have this discussion with you, I just want you to think about it yourself. How would you define a circle? It's round, right? Okay, well, besides that, like how would you describe the set of points that make up a circle? Turns out that this definition that we can use for a circle is the set of all points that are equidistant from this common point. So if I have this point, which is the center of the circle, if I take, for instance, the set of all points that are that far away, then that would be that point, and then this point, and then this point, and then this point, and then this point. If I take the set of all of those points that are equidistant from the center, I would get a circle. And the definition of an ellipse is very similar. So here's our definition of an ellipse, which is 8.2. An ellipse is the set of all points whose distances from two fixed points. So instead of just having the one center like a circle does, the ellipse has two fixed points. And we're fixing them, and then we're using them to focus our ellipse. So these are both called foci. Some people say foci, some people say foci, I don't know, or foci. So we're going to call them foci or focus points. But the pronunciation there is a little bit ambiguous. You've got a little bit of play there. So the distances from both of those points, they would have a common sum. So if you add up the distances from those 2 points, there's a really neat video that I have put in the playlist. It's just a minute long that is showing you how you can construct an ellipse using string, which we would normally do on the board. So for sure, check that out, because I think that that'll make the definition make a lot more sense for you. So the anatomy of an ellipse, just like we have done the anatomy of a parabola yesterday. So there's your ellipse for purposes of our drawing, at least. So you've got lots of things happening here. So the ellipse has a center, and then the endpoints of the ellipse that are on the same axis as the foci, those are called the vertices. These other 2 points, though, the endpoints on the perpendicular axis, they don't have any specific name. They could be called the minor axis endpoints. The axis that has the vertices and the foci is called the major axis. So major axis is from vertex to vertex. If it starts talking about the length of the major axis, then that would be from vertex to vertex. If we talk about the semi-major axis, then that would be from the center to a vertex. The prefix semi means half, right? So from the semi-major would be half of the major axis length. Then you've got the minor axis. And then half of that would be the semi-minor axis, so that you know what those are. And then we also have some distances that we label with the letters A, B, and C. So the distance from the center to the focus is C. And the distance from the center to the vertex is A. And then the semi-minor axis distance here, we're going to label with a B. So the capital letters, the capital F, V, and C, those are points, but these lowercase a, B, and C, those are just lengths that we're going to use so that we can write the equation template for our ellipse. So using this template, and also we're going to go ahead and give the center some points, some coordinates. The center is going to be HK. Then using this, we now can make an equation template for our ellipse. Just like a circle has the x coordinate squared plus the y coordinate squared equals a constant, the ellipse has the same. So the ellipse equation would be x minus h quantity squared plus y minus k quantity squared. But instead of this equaling r squared, because we don't have a constant radius on each side, we're going to think about going ahead and just letting that equal 1. And then both of these, we would be dividing by r squared, you could think of, right? But because they have different radii, turns out that those are different numbers, right? Different coefficients. So x minus h squared would be over a squared in this case, and y minus k squared would be over b squared in this case. And this would be the template for our ellipse equation. This is because the ellipse that I drew is centered horizontally, so the A is in the x direction. If the ellipse was centered vertically, then the A would go underneath the y component. So this picture, the A, which is the distance from the center to the vertex, goes underneath the x because the vertices are aligned horizontally. You'll be able to see an example of, in just a second, of where the vertices will be aligned vertically, and then that's a little bit different. If you look in the textbook, they have 4 different equations, I believe. They have an equation for a vertical and a horizontal ellipse centered at 0, 0, and then a vertical and horizontal ellipse centered elsewhere. And I just want to make it a simplified equation, so just remember that whatever number underneath is the square of that component. So however far you're going in the x direction or the y direction, respectively. Let's do some examples. Oh, also, hold on. Turns out that ellipses satisfy a Pythagorean identity, but it's not the one that you would normally think of. So if we look at A, B, and C, think about, from this picture over here, think about which one is longer, longest, A, B, or C. Turns out that if I take this A length, and let's just move it. I'm going to rotate it a little bit, and then I'm going to move it up here. Turns out that if I would have drawn this ellipse correctly, that A exactly fits as the diagonal of the B and C that are making a right triangle there. So all ellipses satisfy this Pythagorean identity. Ellipses, Pythagorean identity, that b squared plus c squared is going to equal a squared. This is obviously not the normal Pythagorean identity where c is the hypotenuse, so you just have to remember that the a is always going to be longer than c here because a is the distance from the center to the vertex, not from the center to the focus. And so because of that, a is always going to be the longest one, which is the hypotenuse. Okay, so I've got some examples for you. In this case, we have this equation. Let's go ahead and put that in standard form by dividing both sides by 144. So I get 9x squared over 144. But 9 144ths actually reduces to 1/16. And then let's divide 16y squared by 144. But 16 144ths actually reduces to 1/9. So we get the equation x squared over 16 plus y squared over 9 would equal 1. That can tell me that my center has to be at 0, 0 because there's no hk coordinates that I can see here. Then I've got a 16 on the bottom of the x, which means that the distance that I must go in the x direction is going to be 4 units. And I've got a 9 underneath the y, which means the distance I'm going to go in the y direction would be 3 units each way from the center. And then using that, I can go ahead and say, okay, so that's ballpark what my ellipse is going to look like. Try not to make it too pointy, try and make it a little bit more round than what I just did. Then we can use that to say the bigger one is A. So A is 4, which means that B is 3, And before you just get going and say, oh, that means C is 5, Pythagorean triple, remember C is not the hypotenuse here. So we would say C squared plus 9 equals 16. So C is actually going to be the square root of 7. So now let's go ahead and fill these in. The vertices would be 4, 0 and negative 4, 0. I know that it's those and not the others because that was the longer distance. And then the foci would be at square root 7 away from the center on the same axis that the vertices are. Root 7, I don't expect you to take a calculator and know what that is, but I know that root 4 is 2 and that root 9 is 3. So root 7 is in between 2 and 3, and you would be expected to place those correctly in between 2 and 3 units away from the center, that we would go ahead and have those as our focus points. So I can label those that those are foci, sorry for the handwriting, and then that these are the vertices, and then obviously that's the center. So the foci would be at root 7, 0, and negative root 7, 0. And then we're done. We've got all the components and we did what the question was asking. So here's one that they all just kind of give us different pieces of information. So in this one, if the foci are at 0, negative 3, and 0, 3, then I can go ahead and plot those. And if I split the distance, then that tells me that the center is going to be at 0, 0 again. And then it says the minor axis has length 4. So that means that I must be from the center going 2 units each way in the direction that does not have the focus. The focal axis is the length from focus to focus, and that's the same axis as the major axis. But remember then here that these are focus points. Those are not endpoints of my ellipse, so I still have to find the other 2 points. Because those are the focal points, I know that C is 3, because I'm going 3 units from the center to get to the focus. And I know that B, which is the smaller distance and the one that's not on the major axis, would have to be 2, because it said that the minor axis has length 4. And so then using the Pythagorean theorem that B squared plus C squared equals A squared, I get that A would equal root 13, because that's 9 plus 4. And so root 13 I know would be in between 3 and 4 units. So I would go in between 3 and 4 units from the center to get to the vertices. So the vertices would be at, just looking at the graph, I can see that that would be 0 positive root 13 and 0 negative root 13. So now I have all of those, and now I just need the equation. So it's centered at 0, 0. So this would be x squared and y squared. And the x distance that I'm traveling is 2, so I'll put 4 on the bottom there. And the y distance that I have to travel to get to the vertices is root 13. So a 13 is what would go on the bottom there, and that would be the equation that would match that ellipse. The textbook, I believe, puts the bigger one first, the one with the vertices, which would in this case be the y. But it doesn't matter because addition is commutative. So I always just like putting the x first to have them in alphabetical order. It's up to you which one you would want to do. Here's one, go ahead and try this one on your own. So pause the video and I'll also pause, and then we'll go over it in 3, 2, 1. All right, hopefully this is what you've got. So the major axis endpoints, turns out those are just the vertices, a fancy way of saying the vertices to make sure that you were paying attention. So I put the vertices on, and then I found that the center was 3, negative 1. If the minor axis has length 8, then that means that B would be half of that, which is 4. So that's how I found the 2 minor axis endpoints. And then I did the Pythagorean identity to get that C must be 3, which would put the foci at 0, negative 1, and 6, negative 1. And then I made the equation. So I said using the center, which was HK of 3 and negative 1, that's how I found the coordinates there, and that the 5 distance that I was going was in the x direction, so 25 went underneath the x component, and the 4 that I was going was in the y direction, so 16 went underneath the y. And I have everything that I need to have, so there you go. Okay, last but not least, eccentricity. The word eccentric, if you've heard it, means a little bit strange, a little bit weird, different than everyone else, right? Belle's dad in Beauty and the Beast was considered eccentric. So eccentricity is a measure of how eccentric your ellipse is. And we have this equation that says the eccentricity of any ellipse is whatever C is over whatever A is. And for an ellipse, which one is bigger, C or A? For an ellipse, A is bigger than C because you're going farther to get to the vertices than you are to get to the foci. So for an ellipse, the eccentricity is going to be in between 0 and 1 because A is bigger, so the denominator is bigger. Turns out that an ellipse eccentricity of 0, think about it, what ellipse would be the least eccentric, the least weird or strange? Turns out that an eccentricity of 0 is a perfect circle, because the circle is not eccentric at all. It's perfectly normal and beautiful. So that means C, which is the distance from the center to the foci, is 0 for a circle, which means that actually if you take the 2 foci points and you focus them together into 1, then that's what is going to create the perfect circle there. Notice that the eccentricity cannot be 1 because C cannot be A. In fact, if C is equal to A, that's actually what would give you a parabola. And a parabola's eccentricity is always 1. We didn't talk about that yesterday because there was no need to talk about eccentricity for parabolas because they all have the same eccentricity and they all have an eccentricity of 1. A couple real world uses of ellipses. One is a lithotripter, which is emits shockwaves underwater to break up kidney stones. So I myself had a bunch of kidney stones in the fall, and although I have not done this, I have talked with the doctor about potentially some ways to break up kidney stones. One is to just raise the acidity in your blood. Another is using ultrasound, and then in this case, this is you're underwater, and what happens is if they put the source of the shockwaves at one focus and your kidney at the other focus, then when the shockwaves are bouncing off the ellipse from one focus, they will always bounce exactly to the other focus, which is super cool. Another one is if you've ever been to Grand Central Station in New York City, there's the Whispering Arch. And so huge train station, lots of traffic, lots of people. But if you find the Whispering Arch, which is in one of the tunnels at Grand Central Station, the ceiling is actually shaped as an ellipsoid, which is an ellipse that is spun on its axis to make it 3-dimensional. And so because the ceiling is an ellipsoid, you can stand in one corner of the whispering wall and you can face the wall and you can whisper. And even though it's all super noisy and everything, the sound will travel up and around the ellipse and it will get to the other focus point, which would be on the other corner. And it says it's a good 10 meters away as well. And so if you haven't been there, then put that on your list of things to do if you go there, is to find the Whispering Arch in Grand Central Station. You have a worksheet on Teams now that you can do, and I hope that you enjoyed our ellipse video. Bye.